This quiz tests your knowledge of the ledoitwolf shrinkage method, a technique used to estimate covariance matrices, especially useful when dealing with lots of variables. We'll look at several statements about this method and decide which are true. I'm asking you to identify which of the following statements correctly describe the ledoitwolf shrinkage estimator. Think about its properties and how it works. I find that calculating the sample covariance is straightforward. However, the ledoitwolf method requires extra calculations to find the optimal shrinkage intensity, making it slower. It's a trade-off, more computation for a potentially better result. The core idea behind ledoitwolf is to improve the sample covariance matrix by pulling it closer to a simpler target matrix, usually a scaled identity matrix. This, shrinking, helps reduce noise and improve accuracy, particularly when dealing with many variables. Think of it like averaging, you get a more stable result. I like how the ledoitwolf method figures out the optimal amount of shrinkage automatically. It analyzes your data and adjusts the shrinkage intensity accordingly. No need for guesswork or manual tweaking. This is a big advantage. I'm excited to tell you that the ledoitwolf method ensures the resulting covariance matrix is always positive semi-definite. This is a crucial property in many applications because it prevents issues that can arise with negative eigenvalues, often seen with standard sample covariance matrices, especially when you have many variables. It avoids problems down the line. This question asks you to identify the correct properties of the ledoitwolf shrinkage estimator, a technique used to improve covariance matrix estimation, especially in high-dimensional datasets. I will guide you to understand the key characteristics of this method. This statement is true. Calculating the sample covariance matrix is straightforward. However, the ledoitwolf method requires an extra optimization step to determine the optimal shrinkage intensity, making it computationally more intensive. That's right. The ledoitwolf method works by shrinking the sample covariance matrix towards a target matrix, often a scaled identity matrix. Think of it like finding a middle ground between the sample covariance matrix and a simpler, more stable matrix. This process helps to reduce noise and improve the accuracy of the covariance matrix estimate, especially when dealing with high-dimensional data. Absolutely. One of the great advantages of the ledoitwolf method is that it automatically calculates the optimal shrinkage intensity using the data itself. You don't need to manually tune any parameters. This makes the method convenient and efficient. This is a crucial property. A positive semi-definite covariance matrix is essential for many statistical applications, like portfolio optimization. The ledoitwolf method guarantees this positive semi-definiteness, unlike the standard sample covariance matrix which can sometimes have negative eigenvalues, creating issues in subsequent analysis. I see this refers to how the ledoitwolf method figures out the best amount to shrink the sample covariance matrix. It doesn't use a preset number. Instead, it looks at the data itself and calculates the optimal shrinkage intensity. This is a really cool feature because it means I don't have to guess or manually set this parameter. It's all automatic. Isn't that neat? This is the matrix that the ledoitwolf method shrinks the sample covariance matrix towards. Often, it's an identity matrix, a square matrix with ones on the diagonal and zeros elsewhere, that's scaled by the average variance. Think of it like this. The sample covariance matrix might be noisy and unreliable. The shrinkage target is a simpler, more stable alternative. By moving towards this target, I'm reducing the noise and getting a more accurate estimate of the true covariance matrix. Makes sense? This is a fancy name for a method that improves upon the regular way of calculating covariance. It's a smarter way to estimate the covariance matrix of financial time series data. It's especially helpful when you have a lot of variables, high-dimensional data, which is common in finance. The sample covariance matrix isn't always reliable in those scenarios. ledoitwolf tackles that problem. This is the standard way to calculate covariance. It's a simple calculation. But it can be unreliable when I'm working with high-dimensional data. Think of it as a basic, straightforward approach, but it can be less accurate. That's why ledoitwolf was developed as a superior alternative in many cases. This is the topic of the multiple choice quiz. We're focusing on understanding how the ledoitwolf method, a specific way to estimate covariance matrices, works within the scikit-learn library in Python. This is the core question. I need to carefully evaluate each statement to determine its accuracy based on my knowledge of the Ledoit-Wolff estimator. This statement is true. Calculating the sample covariance is straightforward. However, Ledoit-Wolff involves an optimization step to find the best shrinkage intensity, making it computationally more demanding. This is also true. The Ledoit-Wolff method doesn't just use the sample covariance directly. It shrinks it, making it less variable, toward a target matrix. This target is often a scaled identity matrix, helping to improve the accuracy of estimates, especially with many variables. This is a key advantage of Ledoit-Wolff. I don't have to manually tune a parameter. The algorithm figures out the optimal shrinkage intensity itself using the data provided. I'm talking about a special method used to estimate a covariance matrix. A covariance matrix shows how different things in a dataset change together. The Ledoit-Wolff method is great because it improves the accuracy of this estimate, especially when you have lots of variables. It does this by cleverly combining a regular covariance estimate with a simplified version, making it more reliable. This is a multiple-choice question testing your understanding of the Ledoit-Wolff method, specifically how it works and its properties. We're looking at 4 different statements and figuring out which ones are true. This statement says that Ledoit-Wolff is slower than the standard way of calculating the covariance. That's absolutely correct. The standard way is simple, but Ledoit-Wolff needs to perform an extra step to find the best combination of the estimates, hence adding to the computation time. The core idea here is that Ledoit-Wolff takes the usual covariance estimate and shrinks it, moves it closer to a simpler target. This target is usually a diagonal matrix with the average variance along the diagonal. This shrinking reduces the impact of noise and random fluctuations in the data, which makes the covariance matrix more stable. The great thing about Ledoit-Wolff is that it figures out, by itself, how much to shrink the covariance estimate. It's not something you have to manually set. It adjusts based on the specific characteristics of your data. This is a basic way to estimate a covariance matrix directly from the data. It's simple to compute, but it can be unreliable, especially when dealing with many variables and limited data points. This is why methods like Ledoit-Wolff are crucial. This refers to the process of moving the sample covariance matrix towards a simpler, more stable target matrix. The goal is to reduce the impact of noise and create a more reliable covariance estimate. Think of it as smoothing out the estimate to remove the bumps and wobbles. This is the final output of the Ledoit-Wolff method, a covariance matrix that is improved over the sample covariance matrix. It is more reliable, positive semi-definite, meaning it only has non-negative eigenvalues, and generally produces better results for downstream applications. This question tests your understanding of the Ledoit-Wolff method, specifically how it improves the sample covariance matrix, especially with lots of data points. I'm looking for you to identify the key properties of this estimator. Think about positive semi-definiteness, computational cost, the target matrix, and how the shrinkage intensity is determined. This is true. Calculating the sample covariance is straightforward. But Ledoit-Wolff finds the best shrinkage intensity, which adds more steps and thus, more computing time. Absolutely true. That's the core idea. Ledoit-Wolff takes the sample covariance matrix and moves it closer to a simpler target, usually an identity matrix multiplied by the average variance. This is a great way to reduce noise and improve accuracy, particularly when dealing with many variables. This statement is correct. The beauty of Ledoit-Wolff is that it automatically figures out the optimal shrinkage intensity using the data itself. You don't need to guess or manually adjust any parameters. That's a huge time saver and improves the efficiency of the process. This is true. The Ledoit-Wolff method makes sure the resulting covariance matrix is always positive semi-definite. This is very important because it avoids problems that can happen with the sample covariance matrix, especially when you have high-dimensional data. This refers to the actual algorithm of Ledoit and Wolff that's used to calculate the shrunken covariance matrix. I won't go into the mathematical details here, but it's essentially an optimization process that balances bias and variance to get a better estimate than just using the sample covariance directly. This is the result of the Ledoit-Wolff algorithm, a covariance matrix. Unlike the sample covariance matrix, This matrix is guaranteed to be positive semi-definite and, hopefully, a better estimate due to the shrinkage process.